Hello everyone, my name is Jialin Liu. I'm a PhD student from Dalian University of Technology. I'm also a visiting PhD student at UMass Amherst. Today I'd like to introduce our work, BlinkListener, listen to your eye blink using your smartphone. Eye blink detection plays a key role in many real-life applications, such as drowsy driving monitoring, HCI, and eye disease prevention. Although existing sensor-based and camera-based approaches are promising, they still have many problems, such as intrusiveness, strict lighting condition, and privacy concern. Due to the low propagation speed, acoustic signals enable fine-grained, contact-free sensing applications, from decimeter-level hand tracking to millimeter-level respiration sensing. However, millimeter-level granularity is not enough for eye blink detection, because eye blink detection is much more challenging. The basic idea of our work is that the built-in speaker of the smartphone will emit inaudible acoustic signals. The signals will be reflected by eyes and then captured by the built-in microphone. When eye blink happens, the eyelids cover eyeballs, which will cause a signal variation. The first challenge is the extremely subtle motion. Compared with the respiration sensing, the 0.5 mm eyelid thickness will cause only 10% of the chest movement. Moreover, the reflection area of the eyes is only 1% of the chest size, which will cause a weak reflection. Therefore, the extremely subtle motion will lead to a poor sensing performance. To address this problem, our key insight is that eyeballs and eyelids will cause different reflection signal strength. The eyeballs are water texture, while the eyelids are skin texture. When eye blinks happen, we will receive weaker reflection signals. However, it's still challenging to detect eye blinks due to severe interference. Considering a real-life scenario, there exists environmental interference, self-interference, and embedded interference, which is involuntary head movement caused by breathing and heartbeat. Although the head movement is only 1 mm, it's still large enough to interfere with the eye blink detection. To deal with interference, our solution contains two steps. We first employ FMCW to eliminate multipath interference. Multiple reflections can be separated into different range bins according to the time of flight of each path. We identify the eye reflection by its large phase variation and then zoom into it. Since the eye reflected signals contain head movement, the second step is to carefully model signal variations caused by eye blink and head movement in the IQ vector space. As we can see from the two figures, eye blink will induce a phase plus amplitude variation, but the head movement only causes a phase change. Since these two motions always happen at the same time, the composed signal variation will be an arc with a bump on it. That is, the arc is formed by head movement, and the bump is formed by eye blink. But how to effectively detect this bump? This is a very challenging task because we observed that the detectability of the eye blink bump depends on its viewing position in 3D IQ space. From the right figure, we can see that eye blink is undetectable in this viewing position, while it's obvious in this viewing position. So we can properly choose an optimal viewing position to make eye blink detectable from the head movement. We propose a viewing position scheme which adaptively finds the optimal viewing position by fitting the arc formed by head movement. Suppose we obtain a segment of eye-reflected signals. Previously, we cannot observe the eye blink. However, after changing to the optimal viewing position, we can observe this obvious peak induced by eye blink. This is how we exploit the so-called harmful interference to help us detect eye blinks, which was previously invisible. We further propose an algorithm to detect each individual eye blink in real time to address the third challenge, the sparsity and the periodicity of eye blink. We can see from the figure that 4 eye blinks were detected successfully. We implement BlinkListener on Bela and smartphone respectively. Experiment results show that BlinkListener achieves a high detection accuracy. It achieves even higher accuracy when the smartphone is at a comfortable viewing distance when the user is using it. We also evaluate BlinkListener in different practical scenarios. Our system can achieve robust performance. We also find an interesting result that the performance is relevant to users' eye size. The bigger, the more accurate. So BlinkListener enables eye blink detection using acoustic signals for the first time, and it works well in different practical scenarios. And we believe the viewing position scheme we proposed can be applied to improve the performance of other sensing applications. That concludes our work. Thank you for your attention.